Okay, we are just going to do this last little bit, which is in chapter 29. Let's go grab that. Okay, so chapter 29 has a section on polarization, and that is, I believe, extra credit on your test. Actually, it maybe not be extra credit, but anyway, um, whatever, I'll tell you later. So for your last test, you need to know some polarization. Okay, so with polarization, the idea is like Polaroid sunglasses. Um, the polarization is the idea of the electric fields being oriented in a certain direction. And so this is a property for transverse waves. And for an electric field, it would mean that the waves would all be in, like upright as opposed to upright and sideways. Um, Usually, we're going to compare it to someone shaking a rope. They can shake the rope up and down, they can shake the rope sideways. Um, so the idea is that the wave is in the plane of vibration. Okay, so we've got a plane that we're looking at. Now, unpolarized light has the electric field in many directions. So there are many beams of light. One individual beam will have its electric field in a certain direction. But when you've got millions and millions and millions of photons or beams of light coming towards you from the sun, they're unpolarized, many directions. Now we can represent it like this. That's supposed to show electric fields, okay? Or we can show it like this, like it's coming at you and you're seeing all the different directions the electric fields can be in. Or because we're lazy and it's easy, here's an unpolarized beam of light. We're just showing two beams, one up and down, the other one left and right. And so you can imagine those coming towards you. So that's representing unpolarized light. Okay, so here we've got some unpolarized or non-polarized light that is going to go through a polarizing filter. Now, a polarizing filter has long strands of plastic. And basically, when a beam of light goes through them, then the electric field can only squeeze through in the correct direction. Otherwise, it starts the molecules oscillating and the beam of light gets absorbed. So it's kind of like if you're shaking a rope through a fence, it can get through in a certain direction, but not in another direction, right? So polarizing filters or fences can be set up where here would be like two polarizing filters that are parallel to each other. So the rope that's shaken up and down can get through the picket fence. Whereas in this case, we're looking at one of the fences is upright, but the other fence is tipped over sideways. So the rope that gets through the first part can't get through the second part because it can't go sideways. And so this happens with polarizing beams too. So for a polarizing filter, we usually assume that about 50% of the light gets through from an unpolarized beam. So 50% gets through. And then if it can go through another perfect polarizing filter, well, it's already polarized. So all of that light would get through if it was ideal. Non-ideal, of course, you'd lose a little bit more. So it would get a little dimmer. So, but let me show you two parallel filters. Okay, so when you, um, here you can see my face. Here's another filter, and you can still see my face. It's a little bit darker, right? Okay, so those are two polarizing filters. But the second situation is if I rotate one, well, now you shouldn't be able to see my face anymore. The light gets through the first one, but it can't get through the second one. And as I rotate these around to where they're more closely aligned, you will see more face. And then as I rotate them, now they're at 45 degrees. A little bit of light gets through. But when they're totally perpendicular, no light can get through. So anyway, so polarizing filters are fun to play with. So if you've got polarized sunglasses around, or broken ones that you can break in half, then you can play with polarizers too. Or go buy some filters at American Science and Surplus. Great place. Okay, so does this come in any way as anything useful? Well, yes, it does become useful. And here, by the way, oops, shows a woman with two polarizing filters that are parallel to each other here, so we can see her smile. Here she's rotated one 90 degrees, so we can't see her smile. Here she has put in a third filter that is at 45 degrees, and we can see her smile again, though rather dimly. And so in the homework, I'll go over how this works. But basically, if it's at 45 degrees, then there's still a component of the light that can get through. Not much, but some of the light can get through, even though it's 45 degrees away. Okay, um, so anyway, so yes, so that can still work. Now, how do we use polarizing filters? Well, one place we use them, of course, is over our eyes. And so for one thing, light that reflects off water or windows is polarized light. So we wear sunglasses out on the ocean, and that helps cut down on the light that is reflected up from the water and gets under our hat. And so we can see much more clearly with Polaroid glasses. Now here also, here is light that's reflecting off a window that is polarized. So you can rotate a filter or wear glasses with the filter the right direction, and you will see inside the car now. So the people inside were protected from the glare or reflections, but now they're not. The Polaroid filter has, uh, has gotten rid of those glaring bits of light, the reflections. So sunlight also is polarized as it comes through our atmosphere, as it's scattered. So the blue light we talked about scattering before. And so one of the things that people use filters for is on camera lenses. So this is what your natural eye would see. This is a photograph taken by someone who has used Polaroid filters too much because it looks so unnatural. Notice how much darker the ocean is. The reflections are no longer there. So it's hard to see actually what's going on with the water because you don't see the reflections anymore. And in the sky is darker too because you've taken out some of that polarized scattered light. Okay, now the filters, you don't have to go as dark as the lowest picture. If you've got a polarizing filter on your camera, usually it's adjustable. You rotate it so you can decide how much of the light you're going to take out, because that lower picture looks so unnatural because that's not the way our eyes would see it. That's only seen with the filters in place. Now, polarized moonlight and sunlight is actually used by animals for navigation. It's kind of like a celestial compass. So it becomes handy for animals. And that's another reason, of course, not to leave lights on at night, because animals need to be able to see the natural light. Okay, one of the other places we use them is liquid crystal displays. So let's see, I think this calculator has a liquid crystal component. Um, so um, grab the old calculator and camera. Okay, so as I put the filter over it, you can see how it darkens. If I rotate the filter to a different orientation, oh boy, you can hardly see the numbers at all. It seems to be at a 45-degree orientation, but it does have a polarizing component. Liquid crystals often do, which we'll talk about in a minute. Also, your cell phone is also polarized. So you will, if you're wearing Polaroid sunglasses, sometimes it's a problem for people because they can't see their cell phone very well. At least that's the way it used to be. They've gotten better. It's now usually at 45 degrees. But yes, as you rotate a polarizer around, you can often find that there are some angles, oops, I think we're just calling someone, where you cannot see things as well. Sorry about that. It works better sometimes. Yeah, this one, when it's like this, you can see how it's nearly black. And as I rotate, you can see it. Okay, so so if you're watching your phone the wrong direction, your polarized lenses may cause problems. So iPads and things like that are often polarized also. Anyway, so I was saying that liquid crystal displays are polarized. And so these are actually where liquid crystal, what it does is it naturally rotates a beam of light, the electric field of the beam of light. So it rotates at 90 degrees. So there was a beam of light with its electric field this way, and then it got rotated the other direction. Okay, so it rotated at 90 degrees. However, so that's with the voltage off. So it naturally will do that. And so you have your upper polarizer and your lower polarizer, which are in 90-degree angles to each other. That allows light to get through. However, if you turn on the voltage, then what happens is the beam now won't polarize, and so it can't get through the bottom polarizer. It's in the wrong direction now. And so that's how a liquid crystal display on a TV works too. There are some TVs like that. And so each pixel, red, green, and blue, has this liquid crystal that turns it on and off. That's basically what it's there for. So when voltage is applied, then the light will not rotate, so it can't get through the filter, and so that would be an off. So that's another way to for a TV to work. Okay, well that is it. That is the last talk. So congratulations and have a great break.